Hey, we're going to start the next section, which is on perpendicular bisectors and angle bisectors. So first, we're going to start with perpendicular bisectors. So first part is, let's say we are given this line here, and it's perpendicular to this line here. That's the first part we're given. And then, from this, we make points A and B so that AD is the same or congruent to DB. So we're first given two lines at the perpendicular, and then we make points so that the two lines would be congruent to each other. From here, we could connect to make these two triangles. Now we can go on and prove that this triangle here on the left would be the same as this triangle here on the right. We have the same line here, an angle, and the same side. So it's side, angle, side, side, angle, side. So we can go on and prove that here. Now what we can also do, since we've shown that these two triangles are congruent, that means these two sides would also be congruent. So when we have a perpendicular bisector, we're going to have to make sure that these lines here are congruent. So we're going to be able to show that CA is going to be congruent to CB, or CA is equal to CB. So when CA is equal to CB, that means that C is an equidistant point. Now, equidistant means that it is an equal distance from two different points. A to C is the same distance as from B to C. So C is an equidistant point for A and B. Alright, so now we're going to go on and try and go through a couple theorems for this and some examples for that. Okay, so we have the first two theorems, which are just the converse of each other, and they say that it's for the perpendicular bisector theorem and the converse of the perpendicular bisector theorem. So it says, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segments. The converse, if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So let's go for the first part one together. So PM is perpendicular to AB. MA and MB are the same. So that means that PA and PB are going to be congruent to each other or equal to each other. So if we draw a line to P from A and draw a line from B to P, those lines would be congruent to each other. That's what this theorem says. So if you're given the PM is perpendicular to AB and that these two points are congruent, these two segments are congruent, then we conclude that this third one is congruent. The next one is the converse. So first you're given that a triangle with kind of like an isosceles triangle where the two legs are congruent. That means if you draw a perpendicular bisector here, these two lines will be congruent and you're going to be given that right angle here. So that's basically what this theorem says. Now we can't prove that these two triangles are congruent given this side and this side. There is no theorem that shows that. But we can use this to do some other things. So let's go through an example of some questions you might be asked for this. Okay, in this example, we're given a triangle and we're asked to find the length of QR here. So we're told that this line is perpendicular to here, and that these 2 points are congruent. So from just seeing that, from the theorem we just had before, we can now know that QR and PQ, or QP, are going to be congruent because Q is equidistant from R and P. So knowing that, we can set up that 3n minus 1 is equal to 5n minus 7. So from here, 3n minus 1 equals 5n minus 7. So I'm going to add 7 on both sides, and I'm going to subtract 3 on both sides. Then I'm going to divide by 2, and then my final answer will be that n is equal to 3. Then from here, I can plug this 3 back in. It doesn't matter which one I plug it back into because they're going to be the same, but they ask for QR, so let's use that equation. So 5 times 3 minus 7 is equal to 15 minus 7, which is just equal to 8. Okay, so that's for that example there. Now, what we're going to go into next is talking about angle bisectors, but before we do that, I want to just do a quick example with something. Let's say I'm given this line and these 2 points, and I want to find the shortest distance between these 2 points. Sorry, not these 2 points. This point and this line. This point and this line. Well, to find the shortest distance between a point and any line is always going to be the line perpendicular to the point. So point to line, this must be perpendicular. This point to this line must be perpendicular. So we're going to have these things being perpendicular here. Okay, so the next theorem is the angle bisector theorem. This says that if a point is on a bisector of an angle, then the point is equidistant from the sides of the angle. And then we have the converse. If a point is in the interior of an angle, if a point in the interior of an angle is equidistant from the sides of the angle, then the point is on the angle bisector. So what this means is we're given QS here, and this point, and this bisects this angle here. So it makes these into 2 smaller but congruent angles. Then we're told that SP and is congruent to QP. No, sorry, not congruent. SP is perpendicular to QP. SR is perpendicular to QR. So we're given all of this, all of these things. Then that means that SP is going to be congruent to SR. That's that equidistant part of it. Then for the converse. So we're given a point that's on the interior of the angle. That means on the inside part of the angle. And we're told that SP and QP are perpendicular, SR and QR are perpendicular, and that SR and SP are the same length. Well, if we're given all of this, that means that if we draw a line from Q to S, that line would be the angle bisector of here. That line would make these angles, smaller angles, congruent here. And we're also told that these things will all be congruent. So these equidistant things does a lot of different things. Just being told a couple of these things, we can figure out a bunch more stuff. Alright, we're going to go through one more example, and that will be it for today. Okay, so we're given another example that's similar to the one we had with the perpendicular bisector. So we're given this angle, BCD, and we're told that CF comes through it and makes 2 smaller but congruent angles, and that FB is perpendicular to CB, and FD is perpendicular to CD. So remember from the theorem which we had before, we're given all of these things, perpendicular lines here and here, and congruent angles bisector. That means that this side here, FB, is the same as this side here, FD. So now that we're known that they're the same, we could set it up like this. So 6x plus 3 is equal to 4x plus 9. And then to simplify it, I'm going to subtract 4x on both sides and subtract 3 on both sides. So my next line would be 2x is equal to 6. And then to get x by itself, I'm going to divide by 2. So then x is equal to 3. But they didn't ask for what x is, they asked for what FB is. Now remember, we can use either one of these equations, but let's just use this one. So we're going to plug in 3 for that. So we're just going to get 6 times 3 plus 3. 6 times 3 is 18 plus 3, so we get 21. Okay, so those are most of the things that we're going to be doing with these kind of equations in class and for stuff like that on the test.